All right, so welcome to everybody. At this point, we're recording, so if you want to type your name into the chat, you can do that, and we'll have your record for attendance. Um, so, yeah, I hope everybody's had a good week. I want to make a couple of announcements before we start. So, we basically finished our unit on geometry last time when we finished 2 weeks ago, and so I asked for what people want to do for the topic, and it seems like the number one response was trigonometry. So that is what I'm going to focus on. And so this is with apologies to those of you who were already in the class 3 years ago, or 2.5 years ago when we did a trigonometry unit. So this is going to repeat that to some extent, although we're going to go deeper into trigonometry than we did in fall of 2021, which is when we last did this topic. I do want to say, though, that there were a few requests for calculus-based topics. Some people wanted to see integration, some sequences and series, things like this. So I'm definitely open to doing a calculus-based sequence next year if people want to learn calculus or go over calculus. I know that probably not everybody wants that, and some people maybe really do want that, and because it's not, traditionally part of the high school curriculum. So I'm not going to make a commitment yet for this, but if there's enough demand next year to do topics involving calculus, then I'm definitely open to it. So we'll revisit that again at the end of the semester if people want to have a calculus-based class. Okay. But for now, we're going to do trigonometry, and we'll just try to go, relatively deep into trigonometry while also certainly covering everything that's in the Liberian curriculum. Okay, so that's going to be the topic that we're going to do at least for the next couple of months. And with apologies to those of you who were already in this group in fall of 2021 who may have seen some of this stuff. Okay, but it's been a while since then. All right, so and to everybody who responded to the survey, thank you for your input. And later on, I'll ask some more direct calculus questions if people would like to do calculus, but at the earliest that would be in the fall, not in the spring. Okay, so okay, great. All right, so okay, so let's just start for today. As is usual when we start a new topic, things at the beginning start off a little bit easier because it's something new, so we don't have as much to dig for, and then we get into the more complicated stuff a little bit later. Okay, the good news is that we have been studying geometry, right? And so if you're going to do trigonometry, it's good to know something about the geometry of triangles first before you something about the geometry of triangles before you do trigonometry. So the good news is we've already talked about similar triangles and congruent triangles and circles and all of these topics that are going to be important for the study of trigonometry. Okay, so one more time for the people who just came in, we're going to be mostly focusing on trigonometry for this spring, but there was interest in a lot of calculus topics. And so next year, I would consider making calculus the topic if people want to talk about calculus. But I know there might be some people who don't want to do that. So I'm going to get some further input, coming into next year. Okay, great. So let's just start with the basics of trigonometry, which is trigonometry with right triangles, right? So what do we know about right triangles? Well, every right triangle has one angle in common, right? Because they all have a right angle. So if you want to show that two right triangles are similar, then it's enough to show that the measure of one non-right angle in one triangle equals that of one non-right angle in the other triangle, right? So if I have two triangles here that are both right triangles, so let's say I have a right angle here and another one here that looks like this maybe, with a right triangle here. Now, if I can show, for instance, that this angle over here, let's call it theta, if I can show that this angle theta is the same as this angle theta, then we know, so if these two are equal angles here, this is good enough. This implies that the triangles are similar. Because remember, similar triangles are triangles where all three angles of one triangle match the three angles of the other triangle. But when you have a triangle, once you know that two angles match, then you know that the third angles have to be equal also, because whatever this angle alpha is, we're going to have that alpha plus 90 degrees plus theta is equal to 180 degrees, right? Or in other words, alpha equals 180 degrees minus 90 degrees minus theta. And well, whatever this angle is here, if we call it beta, we have by the same process that beta is going to be equal to 180 degrees minus 90 degrees minus theta. So the only possibility is that alpha equals beta, right? Because they're both given by exactly the same formula, 180 minus 90, which is just 90, minus theta. Beta is also 180 minus 90 minus theta, so they're equal to each other. And so what that tells us is that once you know that you have two right triangles and you have a second angle that's equal in both triangles, then the third angle will automatically be equal in both triangles. Okay, so so anytime you have two right triangles with a common non-right angle measure, this is a common one, so it's the same, then the ratios of their corresponding sides are going to be the same because they're similar triangles. Okay. And what we'll see, I'm going to put one more slide in for this, but what we see is that once you know that the ratios of their corresponding sides are the same, they're similar triangles, this is what you need to know in order for defining trigonometry functions to make sense. It's like, why can you talk about sine of an angle or cosine of an angle? Why does that even work if you're going to say, well, the sine of an angle is the opposite side over a hypotenuse? Who knows that if you drew two different triangles, you wouldn't get a different ratio? And the answer is the reason that doesn't happen is because of similar triangles. So we'll see this in some more detail. Okay, but for now, what we see is that if you've got a right angle and another angle that are the same, then the third angle is automatically the same. Okay? Everybody okay? Questions so far? Okay. Yes, James. Yep. James?
Yeah, no, so like you're saying that if we have two right angle, we already know that one of the angle is always another, which is constant. And the two remaining angle, if you have the number of the other angle equal to the other angle, that means automatically the angle become the next angle are equal, right?
Right. Yeah, so like if you knew that theta was 30 degrees, then you would have that both alpha and beta would have to be 60 degrees. Sorry, I'm not getting you anymore.
So that means a right angle, the value of the angle in a right angle. Hello?
Mm-hmm. So I'm not getting you very clearly.
Yes.
Yes. Oh, much better. Much better. Yeah.
Question.
Princeton,
We are not
hi.
getting, but
Yes.
I want to understand something. So it doesn't matter the direction of the triangle, meaning that the angles are facing at the right hand. So
Yeah.
if the angle is changed, where we find theta, and then we place the second within the triangle, the second triangle, where we find theta, and then we
Yeah.
place the angle there. With the angle remain the same, the
Yeah,
value of the angle
it
will
doesn't matter. So if theta was up here, that's fine. It still doesn't make any difference. Is that what you're asking? Yeah, so if theta was
yeah.
up here and beta was over here, then it wouldn't make any difference. You would still have that beta and alpha are the same. So the angle can be in any location, any orientation.
I'm saying where you have the right angle triangle within the second triangle that I drew.
Yeah. Yeah, here's the right
Yeah.
angle. Yeah.
So yeah, in the second triangle you drew, the angle that is shooting there. Now,
Right.
in place of the angle that is shooting, they'll put it theta there. And then we'll bring in the angle now where the theta is, where the red arrow is pointing at the theta. In the second triangle, we are putting the angle there, and then we'll bring the theta where the angle is. So will A, B, and C corresponding to the first triangle?
Yeah. Right. So, yeah, I mean, so I drew them this way, right? So that we have the theta in this triangle corresponds to the theta in this triangle. The point is I'm using the same letter because I'm claiming that these are the same angle. We're assuming that these are the same angle measure. That's why I'm using the same letter over here. But I could have put theta up here, right? This could be theta, and I mean, I would have had to draw the picture a little differently, but I could have theta up here and theta up here, and then the remaining angles would also be equal to each other. Or maybe I'm not fully understanding the question.
Yeah, yeah, sure. Hello,
Okay. Hello. Yes,
Cousin,
Prince.
the Prince. Yeah,
Yeah.
I think what you're trying to see is just simple. We are working with similar triangle, and
Right.
then from the first similar triangle drawn here, it tells you that if you want to draw this the second one, it should be like the way in which the first one is drawn, but not like taking the angle or taking the theta and then placing different area. I think that will not
Sure.
represent similar triangle. So yeah, so I think that is the point.
Okay, so the idea is it's good for visual purposes to see these triangles in the same orientation as opposed to having one
Yes.
rotated. So that's fine. Yes, that's great. But the only thing I would caution is that sometimes the similar triangles won't be given to you that way. So in fact, we saw a proof of the Pythagorean theorem before where you had to find these similar triangles that were not oriented the same way in order to actually use their ratios. And this gave a proof of the Pythagorean theorem. I can go back over that at some point. So if we're drawing them, then it's nice to draw them in the same orientation. But if you're trying to find them in some context, then they might not always have the same orientation. Okay? So you have to be able to recognize similar triangles, even if one is rotated or reflected in some way from the other one. Okay?
It's understood, sir.
Okay, good. Okay, great. All right. So let me just recall the ratios of sides. If we have two similar triangles, I'll draw them as right triangles just because we're really talking about right triangles. But if I have two similar triangles, one that looks like this and one that looks like this, okay? And if these sides are A, B, and C, well, maybe we'll use the standard Pythag. Usually the hypotenuse is C, so we'll say A, B, and C, and then these angles would usually be C, A, and B. And now if I have these sides are A prime, C prime, and B prime, and this is capital C prime, capital A prime, and capital B prime, then we have the common ratios. We have that A over A prime is equal to B over B prime is equal to C over C prime. And by doing cross multiplying, you can get some consequences of these ratios. So what are some consequences of this? Well, for instance, I could multiply, so if I wanted to compare C over A with C prime over A prime, I could multiply, maybe I'll write this over here. I know that A over A prime is equal to C over C prime. Cross multiplying, that means AC prime equals CA prime. And then I can divide both sides. For instance, I could divide both sides by A and by A prime. And this would give me that C prime over A prime is equal to C over A. Okay? So this is another consequence from similar triangles. So if I have that C prime over A prime, the ratio of these two sides is equal to C over A, the ratio of these two sides. And similarly, you can get that B prime over A prime equals B over A, and you can get that C prime over B prime equals C over B. Okay, these are exercises. Okay, so when you have similar triangles, and especially these, I mean, I'll put in a right angle here, although everything on this page is fine, even if it's not a right angle. We have that you have a lot of different common ratios, right? You have A over A prime is the same as B over B prime is the same as C over C prime. Of course, you could flip those, and that works fine also. And then you also have ways of comparing ratios within one triangle to ratios within the other triangle. So you have C prime over A prime equals C over A, and B prime over A prime equals B over A, and C prime over B prime equals C over B. Okay, so these are all equalities of ratios. And this is good, right? Because if we want to start with some angle theta, right? So if these triangles are similar so that we have the theta angle on both sides, then, well, remember in the future, what do we want? We want to define, say, sine of theta is equal to, well, the opposite over the hypotenuse. Right, so the opposite side over the hypotenuse. And well, if I look at the first triangle, that's saying that the sine of theta is A over C. But if I look at the second, so this is from the first triangle. But in the second triangle, this is A prime over C prime in the second triangle, right? And so, but I want sine to just be a function of the angle, right? So I want to be able to say, what is sine of theta? If theta is 60 degrees here, I want to be able to say sine of 60 degrees. So what is it? Is it A over C from this triangle with a 60-degree angle? Or is it A prime over C prime from this triangle with a 60-degree angle? And the point is, it doesn't matter, because once I know that I have an angle of a particular size, say 60 degrees, then this ratio A over C will always be the same, no matter which triangle I draw. And that's because of similar triangles, right? So this A over C and A prime over C prime are the same. That's exactly this equality here, right? It's the reciprocal of this equality, right? So A prime over C prime is the same as A over C. And similarly, if I wanted to do the cosine, which is going to be B over C, the adjacent over the hypotenuse, B over C is going to be the same as B prime over C prime. And if I want to do the tangent, which is going to be opposite over adjacent, so A over B, then A over B is going to be the same as A prime over B prime. Okay, so when we have these similar triangles, you're guaranteed that the ratio will be the same no matter what triangle you draw. And that's important, because if the ratio were different, then I wouldn't be able to say what sine of 60 degrees is, right? It would depend on which triangle I drew. But the point is, it doesn't depend on it because of similar triangles. So we can actually talk about sine of 60 degrees. This is a well-defined thing. It makes sense. Okay? So what we see from this is we can actually make all of our standard definitions of trigonometric functions here. So we're going to start with an angle that's between 0 degrees and 90 degrees. We want an angle like this so that it can be an angle in a right triangle. And we draw a right triangle with one angle labeled as theta. So I'll just draw it right over here. Standard drawing. This is our right triangle and one angle theta. And instead of calling the sides A, B, and C, I'll label them op for opposite, adj for adjacent, and hype for hypotenuse. And then we define all of these standard trigonometric functions by these ratios. So sine of theta is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, tangent is the opposite over the adjacent, cotangent is the adjacent over the opposite, secant is the hypotenuse over the adjacent, and cosecant is the hypotenuse over the opposite. So it's all 6 possible ratios that you could find between these 3 sides. And these are what all of the trigonometry functions are. Okay? And what we've seen from these similar triangles is it doesn't matter what triangle I draw. As long as I have the correct angle theta and it's a right triangle, then these ratios will always be the same, no matter what triangle I draw. Okay, so this is how we define the trig functions. And if you're trying to remember, there's this SOHCAHTOA mnemonic that helps you remember. So the SO is sine opposite hypotenuse, that's SOH, and the CA is cosine adjacent hypotenuse, that's CAH, and TOA is tangent opposite adjacent, that's TOA. So you can remember SOHCAHTOA, and then the other ones you're going to have to remember which ones are the inverses of which ones up here. All right. And so, as I said before, because we've done all this work with similar triangles, we can actually say that these functions make sense. I can say that sine of 60 degrees takes on some value. Okay. So this is how we define all of the trigonometric functions. And if I drew theta up here, that would be fine also. It's just that this would now be the adjacent side and this would be the opposite side. So you can draw it either way. Usually people like to draw theta down here, but it's just a convention. It's not important. You can do it however you want. Okay. All right. Any questions about these definitions? Okay. Thanks. By the way, maybe I'll mention just one more time, since a lot of people came in. I took the poll of the class, and it seemed like most people wanted trigonometry. That got the most votes. So that's what we're going to be doing this spring. There was some amount of demand for calculus as well, and calculus-based topics, which is not something I'm going to do this spring, but it's something that I'll consider doing next year if enough people want to learn some calculus. So that's the plan for now. So in the fall, if there's enough people who want to do calculus, I might do a calculus workshop. Okay. Okay, great. So these are well-defined functions. Okay. So basic relationships with trigonometric functions. It's easiest to remember, the relationships. And I mean, so this is not incorrect, but probably I should have written this as cotan equals 1 over tan. If we think of sine, cosine, and tangent as being the basic trigonometric functions, then secant, cosecant, and cotangent you can think of as the reciprocal trig functions, because each of them is the reciprocal of one of these upstairs. So tangent and cotangent are reciprocals. That's pretty easy to remember. What you have to remember that's a little bit trickier is that secant and cosine are actually reciprocals, and sine and cosecant are reciprocals. So if you're not thinking, you might think, well, secant and sine are reciprocals and cosine and cosecant are reciprocals, but actually it's the other way around. The sine goes with the cosecant and the cosine goes with the secant. I don't quite understand why it's done that way, but this is just how it is, and it's a universal construction. There is something where the definition of secant has to do with the length of a secant line in some drawing. That's why it comes with. But why do they call one of these sine and the other one cosine? Why isn't this one cosine and this one sine? That I have no idea. I don't know why they decided to use sine for one of them and cosine for the other one. So you just have to remember which ones are the reciprocals. So, and this way, if you know SOHCAHTOA, and then you also know which of these three is the reciprocal of each of these three, then you can evaluate any trig function. Because if it's cosecant of something, you can always just say, oh, cosecant is 1 over sine. So I'll evaluate sine, and then I'll take the reciprocal, right? So that's completely fine. Okay, so any questions about these relationships? Okay. All right, let me just mute. Okay. All right. Okay, so Special values of trig functions. This is a table. This table is worth memorizing. So we will derive them, but it's best not to have to derive them all the time. So worth memorizing. Okay, so to know for these special values, 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees, what are the values of sine, of cosine, and of tangent? This is a table that's worth memorizing, and here's maybe a pattern for sine. So for the sine column, if you notice what the entries are, if I write them in this slightly weird way, the entries in the sine column, well, it's 0, 1/2, √2/2, √3/2, 1. You could also write that as √0/2, √1/2, √2/2, √3/2, and √4/2. And so this is a nice pattern, right? Because the √0/2 is just 0, the √1/2 is just 1/2, and √4/2 is just 1, right? So if you see this, these match the entries in the sine table exactly right, but they make this nice pattern, √0, √1, √2, √3, √4, that give you all of these special values. There's not really any mathematical significance to this. It's just a nice way of remembering the pattern. Okay, so if it helps you remember what the values are, you can use this. And if you don't like that, if that doesn't help you, that's fine too. Whatever you like. If it helps you remember it, you can do it. Okay. So, but it's cute, right? All right. So any questions on it? We're going to go through the 30, 60, 90 right triangle and the 45, 45, 90 right triangle. But in the meantime, this table is worth just knowing. It's like a multiplication table, right? When you have to do 6 times 7, you don't count 6 sevens and add them up, right? You just 6 times 7 is 42. Why is it 42? It's because your brain says 42 before you even have the chance to think, right? So you want the same thing for these trig functions. All right. Okay, so any questions?
Yeah.
Yes, Charles?
Yeah. Good afternoon.
Good afternoon, Charles.
Yeah. Thanks a lot. I just want you to, I've seen the table is good, but sometimes people may not they may not remember, but if you help them to derive, what is in the table, they can, whenever they forget, they can easily derive and come up with those figures.
Yeah, that's what we're about to do on the next 2 pages.
Okay.
But
okay.
Yeah.
Okay. That's
Okay.
good.
Good.
That's
yeah.
good.
No, we're going to derive this. This is not magic. This is not this is not a decree from God, right? This is something that you can derive. So this is but it's still worth memorizing after you've derived it, and then if you need to rederive it, you can. So. All right. So let's look at 45 degrees, okay? We're going to start with 45. So 45, let me just mute so we don't get, okay. So let's start with what's called the 45, 45, 90 triangle. So this looks like this. So we have a right angle here and a 45-degree angle here and a 45-degree angle here. And so what we're going to do is just fill in the sides of the triangle. And what we saw with the similar triangles is that we can just fill in these sides however we want, right? Any triangle will work to calculate the trig ratios. So if I want, I can just declare this side to be 1 unit long, right? So I can just declare this side to be 1 unit. And then what we see is that this is isosceles, right? So these 2 angles are the same. And when you have a triangle with 2 angles that are the same, that means the opposite sides to those angles are also the same. So if this is 45 degrees and this is 45 degrees and this side is 1, then this side here also has to be 1. Okay, so we get 1 and 1. And now, what is this side? If we call it x, we have Pythagorean theorem is going to say that 1 squared plus 1 squared is equal to x squared. or 2 equals x squared, or x equals square root of 2. Okay, so we can fill in this side of the triangle with square root of 2. And now if I just take my angle theta here to be my 45 degrees, then it's very easy to just say sine of 45 degrees is equal to what? Well, it's the opposite over the hypotenuse. That's so. And so that's 1 over square root of 2. And if you want to rationalize the denominator, that's square root of 2 over 2. Cosine of 45 degrees, same way, is the adjacent over the hypotenuse, which is again going to be 1 over square root of 2, which is again going to be square root of 2 over 2. And then tangent of 45 degrees is going to be the opposite, TOA, right? So opposite over adjacent, and that's just 1 over 1, and that's going to be 1. Okay, so if we see we get these values, root 2 over 2, root 2 over 2, and 1, and if you look back at the table over here, those are exactly the values in the 45-degree row, root 2 over 2, root 2 over 2, and 1. Right, this is how it comes. Okay.
Yes, I'm
Yes.
concerned.
Prince.
Yeah, thank you so much. I love this proving. My concern is doing here where we have the 1 and 1. So
Okay.
it's up to you to just let 1 and place it at the opposite and adjacent, or where did you get the 1? The two
Right.
ones, where did you get them from?
Okay, great question. Where do I get the ones from? So the first one, I just wrote down, and I can just call, when I'm trying to find the ratios, trigonometric ratios on a triangle, I can always choose one side of the triangle however I want, right? Because you can think of it like a unit, right? How long is this side? Well, I can just declare it to be 1 unit long because I can just declare my unit length to be the distance from one corner to the next corner, right? So the first one I can just write down however I want. And if instead of a 1, I wanted to write a 3, I can do that too. Because we only care about these triangles up to similarity. And that means for one of the sides of the triangles, you can write down whatever side length you want. It's like if this was a foot, I could write down 1. But if you want to measure it in inches, you could call it 12. It's not going to change what the triangle is, right? So you have the freedom when solving a triangle, when you're just given angles and you're not given any sizes, you have the freedom for one side to use whatever value you want, okay? Because you can think of, if you use a value that's twice as big, that just means you're using a unit that's twice as small. Your units can be anything that you want. So I just used 1 here because it was easy, but you could use whatever number you want. Now, once you've declared the length of one side, then you have no more freedom anymore. Then everything, sorry, James, right? Yeah, so once you've declared the value of one side, then your freedom is gone. Then the triangle forces everything. So once I declared this one, how do I get the other one? Well, I had to use that this was an isosceles triangle with 2 45-degree equal angles. And once I know that, then I know that the side opposite this equal angle has to be the same as the side opposite this equal angle with the 45 and the 1. So once I know that this side is 1, then I have no choice but for the other side to also be 1. That comes from the isosceles triangle. And then once I know that both sides are 1, then I have no choice but to use square root of 2 because of the Pythagorean theorem. Okay? So this is the general rule with triangles. If you're not given any sides, then you can always make one side whatever you want. Once you make that one side whatever you want, then you have to be able to choose the other 2 sides in the right way. And for different triangles, it's going to work differently. All that we know for now is that this is isosceles, so that gives us the 1, and then it's a right triangle, so it gives us the square root of 2. But so far, this is not a systematic way. It's just we choose one side however we want, and then we try to reason what the other sides have to be. We'll see in the 30, 60, 90 triangle that the reasoning is different. Okay, is that okay, Prince? All right.
Yeah, thank you so much. Thank you so much. I got this. I think this where sin square plus cosine square theta is just not the one. I think this where it is from.
Yeah, this is completely related to that. We're gonna focus on that identity next week, But yes, this is exactly where it comes from. So we'll talk about that identity next week.
Thank you
Okay,
so much, sir.
you're welcome. Other 45, 45, 90 questions? No. Hello, yes?
Hello?
Yeah, James?
You get it?
James, yeah, getting you. Not so well, but okay.
Yeah. The similar thing you are talking, if you determine your own number to use if the triangle is given, I use 2, noticing that 2 representatives are giving 2√2 over for the hypotenuse. When solving it came down as 1 over the root of 2. So
Yeah.
that means any number you put there, so when you go by the rules, it will come back, it will come to that same values we remove for 45 degree.
Right. Okay.
Because
So let. Yeah.
45
So.
degree value is 1 over root 2. If you use 2 as a value for the first number and represent for the second number because both are opposite, and we find the hypotenuse, we give you 2√2. When you put it, let's say the opposite of hypotenuse, you have 2 over 2√2. When the 2 cancel out, become 1. The 2 cancel have 1 over the root of 2.
Yeah.
So
Perfect.
I don't say that I also agree. That's not any number you use.
Yeah, so this is great, right? So what you're saying, and this is similar to Kaifala's question, right? Is that what if the two sides are both 3 or both 2 or whatever? So I can draw the same triangle over here. I'll just draw it a little bit smaller. Okay, so again, 45 degrees, 45 degrees. What James was saying is that if I do a 2 and a 2, then by Pythagoras' theorem, I'm going to get 2√2 over here. But I'll still get that sine of 45 degrees is the opposite, which is 2 divided by 2√2. But this is the same thing as 1 divided by √2, because you can cancel everything out. And then this is going to be square root of 2 over 2. And likewise with Kaifala's question, if these were each 3, then no, you can't use √2 for the hypotenuse. You'd have to use Pythagoras' theorem with 3 squared plus 3 squared equals x squared. And you would get that x is the square root of 18 if you did that, which is the same as 3 times square root of 2. So the slogan is you can pick one side however you want. But once you scale up one side, it's going to change all of the other sides. So if I use a 3 here, this is going to be a 3, and this is going to be a 3 square root of 2. Okay? And then James Va asked, how do I get this? This is the rationalizing the denominator. So I'll just do this down here. If I do 1 over square root of 2, I can multiply by square root of 2 over square root of 2. That's just multiplying by 1. And if I do that, I get a square root of 2 in the numerator. And then in the denominator, √2 times √2 is 2, right? So that I just get 2. So that's why these two things are equal to each other. Okay. All right. Other questions on this?
I think it's clear, very much clear to me, sir. Because I just use 3 even, placing 3 in a value and giving the same answer. It's clear.
Good. Okay. Great. Okay, so let's move on to the next triangle. So the next triangle is this 30, 60, 90 triangle. Okay. Okay. So this is going to be my right angle. This angle here is going to be 60 degrees, and this angle is going to be 30 degrees. Okay. And again, I'm going to pick a side that I'm just going to label as 1. Okay. Remember, I'm allowed to choose the first side however I want. I could have chosen this side to be 1 or this side to be 1. They all work. Everything will work. We'll get different numbers, but in the end, the trig functions will be the same. So what's the secret here? Sorry, I got to mute everybody. It's loud. Okay. So what's the secret here? Well, the secret is to draw another mirror image triangle right here. Okay, then I'm going to draw also with a right angle here. And since this is the same triangle just reflected, it's going to have the same angles, right? So this is 30 degrees here, and this is 60 degrees here. And let's observe that all angles of the big triangle are 60 degrees, right? Because we have 60 here and 60 here, and here we have 30 and 30, which is also 60, right? Okay, and so that means the triangle is equilateral. Okay. And so let's try to fill in some sides over here. Well, this side here is one. Sorry, Richard, question? Richard or Abraham, question? Sorry, it's a little too much background.
From the side, from the perpendicular line, we have
Yeah.
one on the side.
Yeah, well, so all that I've labeled so far is this one right here. This one is this side right here. This is one.
Yeah.
Yeah. Okay.
Yeah, so plus side will be one.
Right. So this side also has to be one, right? Because this is just a reflection, right? So if this is one, then this is also one. Great.
Okay, so if we have 2 down there,
Yeah.
then the other side will be 2, 2.
Exactly.
Because we have triangle.
Exactly, right? This is an equilateral triangle. So once we know that the bottom side is 2 in total, then that tells us that the other two sides both also have to be 2. Okay. And then how do we figure out the height of the triangle?
So we have to find the height of the triangle. Now we take one of the right angle triangle.
Mm-hmm.
We take one of the right angle triangle to find the height.
Right.
Okay, so we use the Pythagorean theorem to find the height.
Exactly.
By saying 2 square minus 1 square is equal to x squared.
Right. So I'll write the same thing, just slightly different. I'll just write it as 1 squared plus x squared equals 2 squared, which is the same thing as exactly what you wrote. So x squared is equal to 2 squared minus 1 squared. And so this tells us that x squared equals 3 and x equals square root of 3.
Square root of 3.
Great. So that's exactly perfect. So this is, I'm going to write it as square root of 3 here. Okay, so now we have this right triangle. We've solved the triangle. We know all the sides and all the angles, right? We've got 1, we've got square root of 3, and we've got 2. So for instance, if we want sine of 60 degrees, that's going to be what?
Root 3 over 2.
Exactly. So this is going to be square root of 3 over 2. Cosine of 60 degrees will be
1 over 2.
Exactly. So adjacent over the hypotenuse, which is 1 over 2. And tangent of 60 degrees is...
will be root 3.
Exactly. So opposite over the hypotenuse, which is root 3 over 1, which is just root 3. Okay? And you can do the same things with 30 degrees. Maybe I'll leave that as an exercise, but you can do 30 degrees also with this same triangle. You can figure out the sine of 30, for instance, is the opposite over the hypotenuse, which is 1 over 2, and so on. Yeah, so this is perfect. Thanks, Abraham. So this is how we do a 30, 60, 90. Okay, so the way we do a 30, 60, 90 is by starting by labeling one side 1, and then we draw this equilateral triangle. It's kind of a trick. And having that equilateral triangle lets us fill in, we can use reasoning from geometry and then Pythagorean theorem to fill in all of the sides that we need. And once we have these sides, we can calculate all of the angles. Okay.
Yes, sir. Yeah.
Question? Yes. Yes, Prince.
Yeah. Yeah. My attention has been due to where we have the basis, and then the basis we have for the first one we have 1, and here we have 1. Now it gives us 2. Very good.
Yep.
But
Yep.
placing this value into the Pythagorean theorem, now we using just 1. Why we couldn't use the 2? Because it already sum out to 2.
Because remember, the Pythagorean theorem, you need a right triangle to apply it. So this big triangle is an equilateral triangle. It's not a right triangle. So you can't use the Pythagorean theorem. Okay? To do the Pythagorean theorem, you need to have an actual right triangle. So I'll highlight it in green here, right, you need an actual right triangle over here, right? The whole thing's not a right triangle. You have to use this one. And in this one, the sides are 1 and 2. And, well, we didn't know it yet at the time. We'll just call it x. So they're 1, 2, and x. So if you're going to use Pythagorean identity, you have to have 1 squared plus x squared equals 2 squared. Okay, you can't apply it to the big triangle. You have to use one of these half triangles.
Okay, thank you. It can be applied to the big triangle. Also, thank
Exactly. Yeah, you need a right angle. Otherwise, Pythagoras' theorem doesn't work.
Okay.
Great, thanks. So sorry, I see a question in the chat from James Va. Is it possible for the x value to end in a decimal? Sorry. Yes, I'm answering a question from the chat first, and then I'll get to your question. So,
Yeah.
so first I see a question in the chat from James Va. Is it possible for x value to end in a decimal, especially with imperfect square numbers? So there is a theorem that if you have a number that's not a perfect square and you take the square root, then the decimal will always go on forever. It's going to be what's called an irrational number. So it will never end, but usually when you're using trig, you only need to, if you're using it to measure something, then you only need to know the answer to a certain number of decimal places. So if instead of √3, you want to say something like 1.732, that's probably good enough, even though there are more decimal places there. So yeah, when it's not a perfect square, these things will not end in terminating decimals. And in general, if you take sine or cosine of most whole degree angles, unless you're getting something very special like 1/2, then usually you will get irrational numbers and they won't terminate as decimals. Okay, so James Caselli question, and then Charles.
I'm concerned. My concern is shown to where tangent 90 becomes 0. I'm trying to figure
Okay.
out because
Well, tangent of 90 is not 0.
Angle, hello, get me?
Yeah, I'm getting you.
Yeah. If you look at the right angle tangent 90 degree, the opposite is 2, but the adjacent cannot be proven because the two sides are adjacent to the angle. So I don't know, is that because again the adjacent, that's why I make it 0?
Yeah, so listen, it's a good question. And so let me just go back. For everything that we're doing today with trig, we're always picking an angle that's between 0 degrees and 90 degrees. Okay, so we're not allowed to have the angle be equal to 0 or 90. Now you can define sine and cosine for angles that are 0 or 90, and I wrote them on the table, but we're not going to make that definition until next week. For now, when we're defining things based on right triangles, we have to have an angle that's strictly between 0 and 90, because otherwise we can't draw this triangle, right? If this was 90, then it wouldn't be a triangle. This would just go up forever and the two lines would be parallel. So for now, let's just say 0 degrees, 90 degrees, these are bad angles. We're not going to define any trig functions for them yet. We will, but we'll do it next week. For now, always strictly between. Okay?
Thank you.
Okay, you're welcome. Charles, question? You have your hand raised, question? Okay. All right, if no questions, then we'll move on. So, okay. So here's an example. So for instance, if I have a right triangle, let me go back to blue. So if I have a right triangle like this, and this is a right angle, and this side is 5, and this angle here is 30 degrees, then the question is to fill in the remaining sides of the following right triangle. Okay, so let's call this, I don't know, we'll call it X, and we'll call this side Y. And so we can use trigonometry to do this. So a basic example for trigonometry is, well, I know that I have 30 degrees here, and I know what sine and cosine and tangent of 30 degrees are. So for instance, if I want to do sine of 30, this is badly drawn, sorry. Let me change this because that angle doesn't look like 30 degrees. Let me call it 60 degrees. That's better. Okay, so 60 degrees. So I know what sine and cosine of 60 degrees are because I've memorized them or I can rederive them. So for instance, over here, I know that sine of 60 degrees is equal to x over 5. But sine of 60 degrees, if you've remembered it from the table, is square root of 3 over 2 is equal to x over 5. And so we now cross multiply. And that means that 5 times square root of 3 is equal to 2x. And this means that 5 square root of 3 over 2 is equal to x. Okay, so this gives us one side, 5 square root of 3 over 2. And now you can do the same thing for the other side just using cosine. So cosine of 60 degrees is going to be equal to y over 5, because it's the adjacent over the hypotenuse. We know that cosine of 60 degrees is 1/2, so 1/2 equals y over 5. And so this cross multiply again. And this gives us that 5 equals 2y. And this gives us that y is equal to 5 over 2. Okay, so and this is called solving the triangle, right? You can solve for all of the sides of the triangle. All you need to be given is one side and one angle of a right triangle, one angle other than the right angle. And once you have one side and one extra angle, then that's good enough to solve for all of the other sides. Okay, and you can usually do it with just basic trigonometry. Use some sine or cosine in order to figure out the other two sides. If we wanted to, after I figured out x, I could figure out y using the Pythagorean theorem. That would be okay also. But instead, I can just directly do it using trigonometry. Either way is fine. And you're going to, if you tried to use the Pythagorean theorem here with 5 and 5 square root of 3, you would end up getting, 5 and 5 square root of 3 over 2, you would end up getting 5/2 for the other side. So you'll get the same answer. All right, any questions for this problem? Okay, so this is pretty straightforward triangle solve. Okay, let's do something a little bit not much more complicated. We'll do a complicated angle of elevation problem to finish. But so I should mention that, in road construction or railroad construction, there's an important quantity that's called the percentage grade, which represents the steepness of the road. And so what's the definition? The percentage grade is the ratio of vertical rise or fall to the horizontal distance covered, expressed as a percent. So for instance, if I have a road here that's on a hill, so I have an angle here, the value of tangent of 60 degrees is, we did this back here, right? It's square root of 3 over here is tangent of 60 degrees. Okay. Yep. So if this is my horizontal distance covered, x, and if this is my vertical rise, y, then the percentage grade, which is often written like this, is by definition equal to y over x as a percent. Okay, so this is what the percentage grade for a road is. Anything over like 5 or 6% is going to feel like a very steep road. Okay. So I should also mention there's also what's called the angle of elevation. It can be of a road or really of anything where you're looking up at something. The angle of elevation is exactly this angle over here. Okay, so this is the angle of elevation. And that's the angle that the road makes with an imaginary horizontal line. So if this is the road up a hill and you drew a horizontal line like this, then this angle between them is what's called the angle of elevation. Okay. And then we have a formula. Well, using trig, I have this angle and I have these two sides y over x. Y over x is the percentage grade, but it's also the tangent of this angle, right? The tangent of this angle is y over x, right? So the formula is that the percentage grade is equal to the tangent of the angle of elevation. Okay. So it's two different ways of measuring how steep something is. You can measure it in terms of angle of elevation, or you can measure it in terms of percentage grade. And you can convert from one to the other by using tangent, right? So angle of elevation here, tangent y over x, the percentage grade is the tangent of the angle of elevation, right? Because the percentage grade is y over x. That's the tangent. So for an example, so if a road has a 5% grade, what is its angle of elevation? What you're trying to do is solve, well, let me just rewrite the formula. Rewrite the formula if we let theta equal angle of elevation, then what we're doing is we're going to solve tangent of theta equals 5% or equals 0.05. Okay. And so we'll talk about inverse trig functions in some more detail later on, but for now, let me just tell you that there is an inverse trig function. So you can write theta equals what's called tangent inverse of 0.05. We'll talk about that a little bit more in a couple of weeks, but you can put this into a calculator if you want to, and you get that, let me just see, inverse tangent of 0.05 in degrees is, this is going to turn out to be about 2.86 degrees, roughly. Okay, so a road with a 5% grade has a 2.86 degree angle of elevation. Okay, so not quite. Okay, that at 26.5, that might be tangent of 0.5. That would be a 50% grade. So for this, we need a 5% grade. So you have to use 0.05, right? Okay. So this is relatively straightforward. You have to just use this inverse tangent button on your calculator or on the computer, whatever you're using. Okay, you're not going to be able to solve this on your own. Okay. So I want to do one last example today, which is a little bit more complicated, which is one of these angle of elevation problems that, sometimes you get. These are these kind of tricky problems with two different observers. So this is a word problem involving angle of elevation. So here we have two observers are looking at a tree in the distance, and one is standing behind the other one as they look at the tree. One measures the angle of elevation to the tree to be 30 degrees. The other measures the angle of elevation to be 20 degrees. And so if the distance between the two observers is 50 feet, then how tall is the tree? So step one for this is you always want to draw a diagram. So the way I'm going to draw it is here's the tree. This is what we actually want to measure. So maybe I'll call it H. This is going to be the height of the tree. And now we've got two observers looking at the tree. So one of them is over here, and one of them is over here. And so what I'm going to do is I'm going to draw a line down here passing through each of the observers, and then I'm going to draw the observers' lines up to the tree. Okay. So this is, observer 1, and this is observer 2. And what I'm giving you is that they're 50 feet apart. So this here is 50. One measures the angle of elevation to be 30 degrees. That's got to be the closer one, right? Because this angle is bigger than this angle. And one measures the angle of elevation to be 20 degrees. That needs to be the farther away one. Make sure you get this right. If you switch them, you're going to get a negative answer. The wrong answer. So the closer one always has the bigger angle of elevation, right? Because if you're closer to something, you have to look up more in order to see the top, right? You got to bend your head back further the closer you are, right? So the angle is always going to be bigger when you're closer. It's going to be smaller when you're further away. All right, so this is a right angle. We're assuming, I guess I should have said, it's a tree that is growing straight up. It's not leaning over. It's your right angle over here. And then here is some other distance we don't know that maybe I'll just call it y. Okay, so we have two variables here. We have h and we have y. And in the end, we really only need to solve for h, but maybe along the way, we're going to solve for y also. Okay. So let's write everything down. Well, it seems like the hypotenuses here are maybe not so relevant. Everything in terms of these right triangles is based on the sides, the legs of the triangle. Okay, so what I'm going to do is step 2.
We will have to.
I'm going to write down a trig equation for each right triangle.
Yeah, so the equation will be 2.
Yes, the equations, there will be 2 equations. Right, so for the first right triangle, maybe for this small one, I'm going to write tangent of 30 degrees equals h over y. Okay, so the first one is going to be tangent of 30 degrees equals h over y. This is my first equation. And for my second equation, I have that the tangent of 20 degrees is equal to, well, h is the opposite side. And what's the adjacent side for this triangle?
50 plus y.
50 plus y, exactly. Yeah, we'll go over this again. There's going to be homework on this also, Daman. So here's what we have. So we have tangent of 30 is h over y, and tangent of 20 is h over 50 plus y. So I can now isolate h, right? So, or I can write y tangent of 30 degrees equals h, and 50 plus y tangent of 20 degrees equals h. Okay. Now I can, so for step 3, if I want to, this is maybe not the most efficient way to do it, but I think it's easier than doing the other way. So I'm going to eliminate h. I'll go to another page on this, but since these are both equal to h, that means they're equal to each other. So we get that y times tangent of 30 degrees equals 50 plus y times tangent of 20 degrees. Right, I'm just setting these two sides equal to each other. Okay, so y tangent 30 is equal to 50 plus y times tangent 20. So I'm going to have to add in another page because there's not enough room here. So let me rewrite this again. So we have y plus, so we have y tangent of 30 degrees is equal to 50 plus y times tangent of 20 degrees. And if we want to write this out, this is the same as 50 times tangent of 20 degrees plus y times tangent of 20 degrees. So from this, I can get all the y's on one side. So I have y times tangent of 30 degrees minus y times tangent of 20 degrees equals 50 times tangent of 20 degrees. And now I can pull out a y times tangent of 30 degrees minus tangent of 20 degrees equals 50 times tangent of 20 degrees. And now lastly, I can solve for y. So y is going to be 50 times tangent of 20 degrees divided by tangent of 30 degrees minus tangent of 20 degrees. And so this, of course, we need a calculator. Let's try to just write this out as a decimal point. So 50 tangent 20 degrees, 50 times tangent 20 degrees divided by tangent 30 degrees minus tangent 20 degrees. Okay, I am getting here 85.29. Seems about right. Seems reasonable. I think that's right. Okay, so this, I think I get 85.29 here. And so now, step 4 is solve for h. We know what y is, but the question asks, how tall is the tree? That's h. So step 1 was draw the diagram. Step 2, write down a trig equation for each right triangle. Step 3, eliminate h. I should say eliminate h and solve for y. And then step 4 is going to be to solve for h. But that's pretty easy because we have y times tangent 30 equals h. So it's easy and we know y, so we can easily solve for h. So in this case, we have y times tangent of 30 degrees equals h, but y equals 85.29. So h is equal to 85.29 times tangent of 30 degrees, which is, if you remember your table, it's 85.29 times square root of 3 over 3. And let's keep everything in decimals just to make it a little easier. So 85.29 times tangent of 30 degrees is going to be 49.24. Yeah, okay. So this is going to be about 49.24 feet. Okay. So these are kind of complicated multi-step questions, right? You have to draw 2 triangles, do a bunch of steps, and then figure things out. So we don't have much more time today, but I'll definitely spend a little bit more time going over this next time because this example went a little bit fast. So we can do that. But let me remind you 4 steps. Draw a picture, write down a trig equation for each right triangle, eliminate one of the variables to solve for the other one, usually the height is the variable that's easy to eliminate for. At that point, you just have an algebraic a linear equation that you can solve. And then once you do that, then you can solve for the height of the tree by plugging it back into one of the original equations. So maybe just because we don't have that much more time, I'll just tell you this. Of course, I'll send everything out. So there's 3 homework exercises. So one is to show that if you have an angle, then sine of that angle is the same as cosine of 90 degrees minus that angle. 2 is suppose a right triangle has a hypotenuse of length 5 and one angle measuring 37 degrees. Then what are the lengths of the other sides of the triangle to the nearest 10th? So this is going to be using right triangles. And then this is going to be, 3 is the hard one. This is the extra practice angle of elevation problem. So 2 observers spaced 400 feet apart look up at a hot air balloon flying between them. One measures the angle of elevation at 40 degrees and the other one measures it at 50 degrees. And the question is, how high is the balloon flying? And the hint is to draw the diagram very carefully. You may want to label the distance on the ground from one observer to the point directly below the balloon. You might want to let that be a variable. Okay, so I'll send these homework questions out later on, and then I'll just say thank you for your attention. So next week, I'll say we'll discuss the unit circle, but we'll also do more angle of elevation and angle of depression. Okay, so we will meet next week. We'll have class next week. It'll be the 23rd. And we'll talk more about these kind of complicated problems over here. Okay, but as always, I'll send out the notes and I'll post the recording on YouTube. And I'll also post everything on my website, which is now functioning again. So remind you if you need to go to my website. This is blogs.baruch.cuny.edu/aobis. So this is my website. Okay, and that's my general website, but there's a link at the bottom to the Liberia page. So if you want the full website, you can do the same thing, but it's http blogs.baruch.cuny.edu/aobis and then /Liberian mathematics teacher training program. So this gets you straight to the Liberia page. And but if you just go to the shorter website, then there's a link at the bottom of the page that goes to the Liberia page. Okay. And so I'll have all of the lecture notes and everything posted there. Okay, so thank you again for your attention. I'll please, if you haven't done so yet, please type your name into the chat so I have your record for attendance. And yeah, so we'll do some more trigonometry next week.
Thank you.
All right, you're welcome.
Hello, Andrew.
Hi, Abraham. How are you?
Bye-bye. Thank you for
Good.
today's class. We hope to see you next week.
All right.
And we say encourage all the teachers to be part of the class. Let us continue coming. And let us take more time to be in class sooner. Then we can get more time to really have good from you. So thank you.
All right. You're most welcome. Thank you for coming.
Thank you, Andrew.
All right. Thank you, Sungay. All right. Thanks,
hoping that
everybody.
next
I will be there next week. Yeah, so we'll try to start. We'll try to start on time next week, and yeah, we'll do some more trigonometry. All right, I'm gonna stop the recording.